So here's the last part of Part D from problem number 4 of the 2014 AB and BC exam. And in Part D, they introduce a second train, Train B. Train B is traveling north from the origin station. At time t, the velocity of train B isn't given by the values in this table, but it's given by this function. So here's the formula for the velocity of train B at any time t. They tell us at t equals 2, this train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. So we want to find a certain rate given other rates. So this is a related rates situation, and anytime we have a related rates problem, we typically like to draw ourselves a picture. So here's the origin station. We have train B, which is traveling north. This distance, the distance train B is from the origin station, is changing over time, so I'm going to label that with a variable. Now at time t equals 2, train A is traveling to the east. We know that because we have positive velocities clear until t equals 5. So we know that train A, is traveling to the east. And since this distance changes as train A moves, we're going to specify that with a variable. The distance between the two trains, if train B is here, train A is here, the distance between is going to be specified by the hypotenuse of this right triangle. So I'll call that C. What we want to find is we want to find the rate in meters per minute at which the distance between them is changing at t equals 2. So what we really want here is we want to know dc dt at t equals 2. So this is what we need to find. How can we find that? Well, what we can do is we can write down a relationship between our variables, and that would just be a simple Pythagorean theorem. And then we can make dc dt appear by taking the derivative of both sides of this with respect to t. So if we take the derivative of that side with respect to t, and then we also take the derivative of this side with respect to t, it's going to be implicit differentiation. A is a function of t, so we're going to do the derivative of the outer function and then multiply by the derivative of the inner function, a. Derivative of b squared is going to be very similar. We're just going to have different variables. So that's going to be db, whoops, I was right the first time, 2b db dt. And then the derivative of c is going to be 2c dc dt. What I'm going to do is I'm going to divide everything by 2, divide both sides of this equation by 2, which basically lets me get rid of all these common factors of 2. And now we want to put values in place of a, dA dt, b, dB dt, c, and we want to solve for dc dt. So we know that at t equals 2, train A is 300 meters east. They told us that in part C. We know that dA dt, the rate of change of train A's position at time t, is given by v sub a of t, the velocity at 2. So I'm putting 300 in place of A. We had that from part B. The rate of change of position, the rate of change of A, is going to be the velocity of train A. And at 2, that's 100. Similarly, we can take 400, the position of train B at t equals 2. Put that in place of B. And then dB dt, well, that would be the velocity of train B at t equals 2. We don't know that, but we can find it real fast here. And we can put 2 in place of all of our t's, and we'd be looking at negative 5 times 2 squared plus 60 times 2 plus 25. And so I think if you simplify this, negative 20 plus 120 is 100, plus 25 gives you 125. And then the value of c at this time, well, if this is 400, whoops, not 4,000, but 400, and this is 300, this is really a 3, 4, 5 triangle, and that's going to end up being 500 at time 2. So we'd be putting 500 here. Now it's just a matter of doing some arithmetic and dividing by 500 to solve for dc dt. So if you do the arithmetic and divide by 500, what you should end up with for dc dt is 80,000 divided by 500. And as long as my arithmetic was right, what you end up with there is 160, and that will be measured in meters per minute. You can go back and you can think about all the dimensions of everything in here, but you know, this is meters. This is meters per minute, meters per minute. This is measured in meters. So you have meters squared per minute in this numerator divided by meters. So our answer does end up being in meters per minute.